Hey everyone, welcome. We'll wait for a couple of minutes to let people in. GM. How are you guys doing this, I guess evening? What time is it for you guys?
Oh, it's 6 o'clock here, 6 p.m.
It's 10 a.m. for me here in Dallas, Texas. And Michael, you're in London?
Yeah, it's 4 p.m. Yeah, I mean, it started for you like early in the morning, right? Today. Crazy.
Yeah. Yeah. Not as early as in Hawaii when I had met with you guys. So it's more doable now. Well, all right. I think this is being recorded, so we'll just go ahead and hop in. Yeah, I want to introduce Maya and Michael from StarkWare. They'll be going over building with Noir. They'll do some basic examples with Noir circuits, and then verifying, and then going into like deployment on their testnet. So I'll let Maya take over and share a bit more about StarkNet and StarkWare.
All right, thanks. I'm happy to be here. So I think I'm going to uh, start off with a bit about Starknet and how this meets Noir and how we can work together. And then I'll pass it on to Michael for the hands-on stuff and more in-depth. So I'm Maya. I'm the product manager for anything proving and privacy related on StarkWare. StarkWare builds Starknet. So Starknet is a ZK rollup over Ethereum. It's Stark based as opposed to Snarks with Noir. It's battle tested and performant. We had recently shown a peak of 850 TPS, I think. And we are going to be fully decentralized. This is our roadmap, both for sequencing and proving. So all Starknet blocks are proven, and they will be proven in a decentralized manner. We will also be an L2 over both Bitcoin and Ethereum simultaneously. This is hopefully by end of year. Cairo is the Starknet language. It's a language and virtual machine extremely performant for proving. It's a general purpose language, so we'll talk about that. And the prover for Starknet is currently Stone. It's moving to Stu, which will be soon rebranded to a different name, but it's the Starknet 2 prover. What about privacy? So even though Starknet is a ZK rollup, it's not truly ZK. So everything is proven, but it's not ZK. So we are aiming to enable as much privacy for users in whichever flavor they need. And that's what we will be talking about today. So as you probably all know, Noir is a DSL for writing ZK programs. Truly ZK, very Rust-like, very nice to interact with, a nice intermediary representation, and supports multiple proving backends, all snarks, which is very nice, very well documented, and very easy to get started with, which is, I'm guessing, why everyone is here today. Cairo is a generic language, so it's Turing complete, which means that you prove, as opposed to Noir, in which you write your code and you get a prover verifier pair. In Cairo, you write your program in a Rust-like language, and you can verify all programs with the same verifier. So it's kind of a different animal. And this is how Starknet operates. And this is very nice for Starknet because you can deploy any contract, and as long as it's written in Cairo, the state of the blockchain can be proven because of its a generic language. And it's Stark-based, or Circle Stark for Stu, which is a different proving system. So where do these two meet? So Noir is a great developer experience, very, very convenient for writing privacy apps, super easy to follow, fast for anything client-side that you need to prove locally, also because you can choose one of the multiple proving systems, small proof size, so really perfect for anything that you want to do client-side for privacy. And where does this meet? Starknet. So Starknet has low fees and native account abstraction, which is very nice for privacy-related stuff, which Michael will be going into soon. It has no trusted setup, which is really nice for a blockchain. So maybe trusted setup doesn't matter for a client-side application, but for a blockchain, it's really great not to have. And with the bridge between these two things is Garaga, which is basically an SDK for a super, super cheap and efficient verification of snarks on Starknet. So it's at least 100 times cheaper than Ethereum. And this is basically what enables us to use Noir as is for writing client-side applications and verifying them on Starknet. So how does this work? Basically, Garaga lets you take a Noir program and auto-generate a verifier contract in Cairo for your Noir program, which means that you are indifferent when writing to whether you're writing for Starknet or not. And you have a verifier in Cairo that's auto-generated, and you can just deploy it on Starknet, which Michael will show soon. It's also nice because it doesn't only give you the verifier circuit, but also it lets you auto-generate everything that you would need for on-chain transactions that you would use to interact with this verifier without having to learn anything other than Noir, basically. And it's super, super efficient for elliptic curve operation. So basically, I'm not going to go into all of the math right now, but I listed some things here today. And it does very efficient EC computation, and it uses hints, which is kind of the Cairo equivalent for unconstrained functions in Noir, in the sense that it uses some non-determinism, so you can give as a hint the result of a computation that you don't want to do directly because it's expensive. So this allows for very, very efficient stuff doing snarks on Starknet. And this is a nice chart by Michael, actually, for showing the entire flow of Noir and Garaga on Starknet. So Noir, you write your program in Noir, you auto-generate using Garaga a Starknet smart contract, you deploy it, and then you would write your Noir program and auto-generate call data to interact and invoke the smart contract. So as you can see, it basically abstracts away any Cairo that you might need to use. So some prices, it's super cheap to verify Noir proofs on Starknet. We have a order of magnitude of 0.04 cents, much cheaper than Ethereum, 100x. And what Michael will show you as well is that because the proof verification is below 1 million Cairo steps, which is, I guess, meaningless to anyone not interacting with Cairo, but it's not a huge amount of computation, which means that you can actually use account abstraction to get a lot of functionality out of Noir proofs by using the verification in validation instead of, well, Michael will go into it. So where does this leave us? It leaves us with a super easy integration between Starknet and Noir. It's very nice, we believe, because it both enables us to decentralize our technological stack, reach more people who love Noir for good reason. And we believe that decentralizing technology will just enrich the ecosystem and drive better results for everyone. I'll say a couple of words about our Stu prover, our new generation prover. So it's kind of state-of-the-art prover. It will prove all StarkNet blocks. We hope to make it also ZK at sometimes in the future, but for now you can use Noir. And I'll just show some benchmarks about performance of Stu. So you can see that it's going to be a game changer for proving StarkNet blocks. It beats state-of-the-art competition, even using precompiles. So Stu plus Cairo's code beats dedicated heirs in competing systems by a landslide, typically. And yeah, so come build with Noir and Garaga on StarkNet. And Michael, to you.
Thank you. Yeah, hello everyone. Michael from Exploration. Yeah, super excited to be here. Thanks a lot to Rafi and all the Noir and Stack team. Thanks a lot, Maya, for the introduction. This to continue with some hands-on session. So it's going to be okay. All right. Yeah, no worries. Maya, could you please share the QR code, like just for a bit, for people to
Oh
scan?
yeah. Yes, sure. Yeah, I will do that. This is not correct. Okay. Yeah.
Thank you.
And I didn't mention, but indeed, Feltroid is responsible for Garaga. So sorry for not mentioning that. And yeah, he's the genius behind it.
Yes. All right. So the so the hands-on session will we'll use Garaga and Noir and Cairo to build a privacy-preserved application on StarkNet. So it will be done in steps. So I prepared some starter. So it's like a simple application with the circuit that does nothing from the Noir quick start, and some auto-generated verifier contracts and simple front end. We will be creating proofs in the browser just to start from something, because it takes time to build things from scratch. And then we will iterate on top. We will first introduce more involved Noir logic in our circuit. Then we can do things in Cairo. And lastly, so we will deploy everything to the public testnet. So let's start. I will share my screen. A sec. Okay. Okay, great. So the like for your operating system specifically. Okay, sorry. I will troubleshoot my issues in a sec. So meanwhile, so please try to install the dependencies. They are like listed in the repo, and I will be back shortly. Okay, great. Okay, cool. Yes, thank you for suggestions. I have turned and turned on my router. Okay, guys. Yeah, sorry for that. All right. So if everyone like up to speed, so you can follow like the steps or just like bear with me. I won't do like any live coding because I'm pretty bad at speaking and writing the code. So I have everything prepared in advance. But we will like go through the code line by one just for me like to explain you what every line means. But before, so we need a couple of dependencies to install so that we can work with the project. So first of all, for the front end, I'm using like a simple React, like a scaffolded project using React and White. And I'm using bun for dependencies. So if you don't have bun, you can install it. There is a nice alias in the make file for you if you'd like. Next, for Noir, so we will need Noir tooling for compiling the circuits and generating the witness. And we also would need the proven backend, the Berentenberg proven backend, so that we could generate the proof. Again, so there are like aliases in the make file for you for the convenience. So note that we need specific versions so that we have all the components compatible with each other. If you have previous installation for like either Noir and Berentenberg, just please make sure that you have these specific versions, or like otherwise you would need to switch. And then for the Starknet, we need also the compiler toolchain in order for us to compile the contracts. It's all nicely packaged in a single installer. It relies on a SDF package manager. So if you don't have it, so that command will install it for you. If you have, then good. And finally, so for us to experiment with smart contracts, we will need local environment. So this is akin to Ganache, or like if you had a previous experience with EVM or other networks, so this is kind of typical thing you would do. So yeah, just also please install this. Right. So couple of words about the project. So it's organized in layers. So we have several Git branches. So in the master, I have a kind of minimal app scaffolded. So it does nothing. So it's a dummy circuit, verifier contract, and some simple front end. And then on top of that, there's like a next branch that adds some logic to the circuits, another branch that adds state on top of that, and finally, we need to do some changes to be able to connect the wallet and do everything on the public Starknet testnet. All right. So the project itself consists of three things, as I mentioned before. So this is the Noir circuit, written in Noir. We will have a couple of contracts written in Cairo, and finally the front end. All right. So pretty straightforward. As I said before, so the circuit is pretty straightforward. So it just asserts that we have two inputs. One is private, another one is public, and we just check that they are not equal. That's it. So this is the example taken from the Noir quick start. And right, so now will quickly show you the flow, like how we go from building the circuits to running the app and proving in the browser. So everything is available in the make file as common aliases. So you can find all the commands in the README step by step. So you can try to do this on your own. I will just do like a quick walkthrough. So the first thing we do is we need to build our circuit. And we have a comment for that. So once we've done that, so we have the output, right? So the circuit represented in its intermediate representation. So this is required for other components. So it's needed for generating the witness, and later for the prover to produce the proof. What we can do next is we can generate the witness, or like in other words, the solution for the set of constraints that our circuit represents. And yeah, so here I have a file that contains some values, actual values assigned to the inputs for private one and for public one. And using those values, we can generate the solution, the witness. And we can also like check that the prover like works okay. So we're using the ultra honk flavor. So this is the one of the flavor of Plonk that is targeted at more like a faster proving speed on the client at the cost of slightly larger proof size and slower verification. But since but yeah, we can still verify honk proofs pretty cheaply on Starknet thanks to Garaga. And yeah, so we can generate the proof. Everything is okay with the circuit and the inputs. And the last thing is we need to generate the verification key. So this is something that we need to hand on to the verifier. It's specific to the circuit. It's not the trusted setup, but it's just like a set of constants that are required to verify proofs for specific circuit. This is something that will live on chain. And this is something that Garaga needs in order to automatically generate the verifier contract in Cairo. And this is something we will do right now. So, yeah. Yeah, I just have some issues with the Scarp version, but so the formatter didn't work, but that's fine. That's not a problem. Right, so Garaga actually has created the entire project for us with all the modules, all the configuration files. So like in Cairo, we have something similar to Cargo. It's called Scarp, and it's basically the same. It's the definition of the package, list of dependencies, and some compiler-specific flags. And yeah, so we have a bunch of Cairo modules. They look quite scary, but that's all right because we don't need to change anything. So it's like ready to deploy smart contract that we can work with as is. But I will like still quickly go through to just explain you what is it we're like looking at. So as Maya said before, Cairo is a generic language. So you can like in theory, you can use it to write anything, but there is a specific framework for writing smart contracts and that we use in Starknet. And all those special attributes that you see here, they are like part of this smart contract framework. And typically, if you wanted to describe smart contract in Cairo, you would start with creating an interface. So this is how your contract would look like for the users. And so it's like a set of methods, public methods, like either view only or the ones that can mutate the state. Second, so this is denoted by the interface attributes. And second part is where you actually implement that interface. So we specify that the following module is our contract. So it's the entry point of the program so that Starknet OS would understand that. And inside that module, so we will have a couple of essential sections for the smart contract. For instance, the storage. So in our case, it's empty, as I said before. So proof verifier contract is a stateless contract, so it doesn't have any state. yeah, so this is essentially the implementation of the interface that we declared previously. Okay, and for the verifier contract, we just have a single method to like verify the proof, and it accepts just like a single variable, which is the serialized proof that we obtain from the prover. And it returns either none if the proof is incorrect, or it returns a list of public inputs in case proof is valid. All right. So yeah, there's like a lot of code. It's quite scary. Don't worry. So like Garaga handles everything for us. Now, what we can do with this contract? In order to use it, we need to deploy it. For that, we need to do two things. So first, we need some environment so that we can deploy our contracts. And the easiest way is to just spin up your local instance for Starknet chain. So we will like use Starknet devnet, and yeah, so there's a nice alias for spawning a local network. You just run that in a separate terminal window, and yeah, it will do it for you. So this is like local chain. It creates new blocks every time you submit a transaction. There are a couple of pre-deployed accounts that we can use for interacting with the contracts, deploying contracts, so it's quite handy. Now I'm going to, so we just need to do one more step to configure the account that we will be using for deployment. So don't worry, so this private key has no real money. It's just some pre-deployed key in the local network. Don't try to, yeah, check out it on the mainnet. And yeah, but please don't use it on the mainnet with real money. So we will be using Foundry. So it's Starknet Foundry tool set for interacting with Starknet for like deploying contracts and interacting with the contracts. And we just need to do some configuration to tell Foundry that this is our local RPC endpoint. This is the file with the accounts we're going to use. This is the name of the account. Yeah, just don't show Explorer links because we don't have Explorer locally. And yeah, so that's enough for us to deploy the contract. So one important thing. So in Starknet, the deployment actually consists of two steps. So first step is called declare, and it's roughly uploading the code of your contract to the network. Okay. Once you do that and your code is uploaded, then you can move to the next step, which is actual deployment, and you sort of instantiate your contract from the class hash. It's called class hash that you declared before. Okay. Sorry, I will just stop a bit to address the issue. Okay. Should the Garaga be installed separately? Should be installed during make install? Okay, yeah, that's a good question. And yes, thank you for pointing that. I think I missed one of the dependencies you need to install. So you need to install Garaga. Yes, you need to do that with Python. Yes, please note that you need this specific version. Yeah, sorry for that. It's usual, you know, like it works on my machine thing. Yeah, please let me know if that worked. Cool. Okay. So circling back to deployment contracts to Starknet, right? So first we declare, then we deploy, all right? So I'm declaring the verifier right now. So that uses SNCast. It's like one of the tool set in Starknet Foundry. And it compiles the verifier contract for me in the release mode. And once it's done, so it will create like a special transaction type and submit to our local development network. Okay, cool. So this is the class hash that we just declared, right? So once we have the class hash, we can deploy. So I have already hard-coded that just for the sake of speed. And yeah, so this is the contract address in our development network. So cool. We're like almost there. So last step is we need to run our application. So, but before that, I will do one more step. So I will copy some artifacts from Noir outputs and Cairo Scarp outputs to the application, because this is necessary later for generating proof on the front end and later to interact with the contract. Okay, so final step, the application. As I said before, it's like a really simple React app. So all the logic is basically in the single file. Yep, in this file. It's pretty straightforward, super simple. And what I have here is I have a state machine that has several stages. So we start from initial, then we generate a witness, then we create a proof, then we reformat the proof so that we can put that into the transaction call data. Then we connect the wallet. This is an optional stage. And finally, we submit transaction to the Starknet. And if everything is okay, so we like reach the proof verified stage. All right. So essentially, those are the same steps we did with Makefile locally, but just now we are going to do that in the browser. So all these steps are written here. It's just one large try catch, again, for just for better understand things. And I have the contract address hard coded here. I will just update it. Okay. And yep, I will run the app. Okay. It's Garaga with A at the end. Okay, so this is the app. Pretty simple. So I have my private and public inputs, and here are the states of the machine that I mentioned before. And yeah, we'll just start the process. It will generate the witness, then the proof, then the call data, wallet, and send the transaction. Okay. So everything worked well. Yeah, just like show you that if you, for instance, provide some incorrect inputs that do not satisfy the constraints, it will result in an error. Okay, so what just happened? We have generated the proof in the browser. With Garaga, we have, yeah, sorry, I will just like go show you here what happened. So we generated the witness. Okay, so we loaded the bytecode and the application binary interface from the circuit, the compiled circuit. Then we created the proof using the Berettenberg backend, using the results of the previous step, the witness. Okay. Now next we reconstructed the proof and serialized. So in a Starknet compatible format using Garaga, we skipped the wallet connection step, right? Because we're just interacting with the local chain. And finally, we called our contract. So remember, I told you that the verified proof is a view-only method, right? So we didn't mutate the state, and there was like no actual transaction. We just invoked the contract, all right? And therefore, so there is no transaction. But it's still, we needed a deployed contract so that we could interact with it. So this is the baseline, all right? So this is the fully functioning application with Noir, Cairo, Garaga, and all wrapped in the React app generating proof in browser, but it doesn't do anything interesting. So we will do one step further and introduce some extra logic to the app. So now, if you are following the process and everything is okay with dependencies and all, you can switch to the next branch, which is called, the app logic, right? And so in this branch, so we will change our circuit a bit, right? So we'll introduce some extra logic. I wanted to do something simple, yet something that would showcase some important concepts. And I wanted to do the following app. I want a contract that would accept integers, but only if they are perfect squares, like 4, 9, 16, 100, 256, like and so on, right? Sounds simple, okay? But on top of that, I want two extra properties. So first, I want my contract to prevent me submitting the same integer twice. Okay, so in case I already submitted 4, let's say, next time if I try to submit 4, it would reject that, right? This is the first property. The second property is that I want to hide from public the exact number that I submit. So whenever I provide like an integer to my contract, it's not clear what is it exactly from the outside, but still the properties should be preserved, right? So it has to be checked that this is the perfect square and no single integer can be submitted twice. Okay, so how do we do that? Let's go one by one, right? So starting from the first constraint, it's quite simple. We just need to check that whatever the input, private input, right? Because we're hiding the integer from the public. It is a perfect square, meaning that there must be a square root that is an integer. And a new way to do that is to implement square root algorithm in Noir. And that would be quite involved program, and it will also have certain limitations. So here we will use one of the, I think, like important concepts in ZK circuits is non-deterministic computation, or in Noir it's called unconstrained functions. The idea is for certain computations, it's quite hard to compute something, but it's quite cheap to verify. And this is true for square root. So while it's quite, well, like the implementation for square root algorithm in Noir would be quite involved, checking that something is equal to a certain number power to 2, it's really cheap. It's just simple single multiplication. So instead of taking square root in Noir, we will just compute the square root outside of the circuit, provide that as a hint, and then we'll just check that this hint power to 2 is actually equal to our input. Okay. So this is a very powerful mechanism, and it's used a lot. It's used in Garaga in order to make it really performant. It's also a source of numerous issues and bugs in the circuit. So if you're using this mechanism, be super careful and just make sure that you understand what you're doing. So here I have really simple binary search algorithm for finding square root. It is unconstrained. The benefits of using unconstrained is that, for instance, I can have unbound loops. This is something you cannot have within the circuit. And yeah, I just check that the my input is a square of some number, and I don't really care like how we obtain this, right? So the only thing I care is that my input is a perfect square. So this is simple constraint. Now, how do I prevent reusing the same integer twice, right? So if my input was public, so that would be quite simple, right? So I will just need to keep a set of used integers in my contract, and every time I submit new integer, I would just check that if that integer like already in the set, that I would refuse that. Otherwise, I would accept and just add to the set. But I cannot do that because my integers are private. So what could I do? First thought might be, let's just take a hash of those private inputs, right? So whenever I submit a number, I would check that the hash of that number is actually in the set or not. And if not, it means I can accept that. The problem with this approach is that although it sort of hides the original number, it's still possible to deduce which ones I used, right? So I can pre-compute as an adversary, like an external observer, I can pre-compute hashes for like 4, for 9, for 10, for 100, like 256, like etc. And every time I see someone submits those hashes, I will instantly understand that someone has provided 4 or I don't know, like any other perfect square, right? So we need to somehow blind this hash or like commitment, right? So we need to blind the commitment. And this is actually a quite common problem in when you develop ZK apps. And the mechanism for resolving this problem is typically is solved by introducing nullifiers. So by name, it's something that nullifies the state. So it's something that tells you that this state has been used, or like this state has been updated, or like the value is no longer relevant. And the way we blind the commitments is that instead of just hashing the numbers, we will hash this number plus another random number. And together, like since this another random number, I will call it secret key, is not known to anyone, now it's impossible for you to pre-compute commitments for certain like possible inputs and deduce which particular square perfect squares I'm submitting on chain. Okay. Okay, great. So last problem remains is that how do I ensure that this is exactly the number, the same number I'm using for all the nullifiers? And in order to enforce that, I need to do something that is called ZK signature. So it's another interesting concept. It's we're used to ordinary like a common signature schemes based on elliptic curves, where our private key is a scalar and the public key is a point on the circle curve. So here, our private key is again is a scalar, it's a field element, but the public key is just a hash of that element, all right? And when you provide a signature, you're just providing a proof that you know the private key that corresponds to the hash of that private key, essentially. And circling back to our nullifiers, if we keep the hash of that secret key of our blinder in the contract, so every time we submit a nullifier, we can actually ensure that this nullifier was obtained using the expected blinder. This is important, okay? In the result, so we have 3 constraints. We're checking that our input is a perfect square. We check that the whatever the public key is, it corresponds to the secret key. So here I'm using this the Poseidon hash function of pair. I'm just using this because we have the same function in Garaga. Other than that, I shouldn't just hash it twice. I could just use it once. And we also check that the nullifier is the hash of the pair secret key and our input. Okay, great. So this is the new circuit. Now we just do the same steps as we did before. So sorry. We will build the circuit. We will generate the verification key. Then we will regenerate the verifier contract. Then what we need to do is we need to redeploy the verifier contract, right? Because now it has different class hash. So we need to recompile and everything. While we're waiting for compilation, so if there are any questions or notes regarding the what we did with the circuit, so please let me know. Okay. Where the secret key start? Okay, so the secret key and the input are private inputs. So that means that they remain on the client side. So they store nowhere. Like of course you need your secret key. You need to keep your secret key so that you can consistently produce nullifiers. So you need to store this there on the client. So in practice, you would this is something that your wallet would do, or you would need to derive this key from your master key somehow. But yeah, we kind of keep this thing outside. But it's actually a very important question because it's kind of this implementation detail that's it's not that fancy and cool. But it's super important because you don't want to lose your blinder key for the nullifiers, otherwise it would be quite troublesome. All right, so we have our verifier declared and we deployed it. So I will just again update the contract address. Everything else stays the same. So we haven't changed anything, right? So our app still stateless. So I will just, I just wanted to make sure that the application runs fine with the new, yep. Yes. So we don't, constraints are not satisfied because the input is not perfect square. And yeah, everything's great. Okay, cool. So now we're moving to the, okay, so now we actually wanted to introduce some state, right? Because we need to keep track of the nullifiers, and we also need to make sure that the nullifier, that the blinder that they use to produce the nullifier remains the same, right? So for those who are following the process, so please check out to the next branch, which is called app state, right? And this is where we will touch the Cairo part. So before, we had just one contract, the verifier contract, and that contract was stateless. So we just use it to verify the proof. Now we wanted to introduce some state, and the of of course, so we could modify the contract that Garaga generated for us, but more cleaner way would be just introduce another contract. And I called it main. And it has just one function that is called add solution. And it also accepts just the serialized proof, right? So remember that everything we need, the public key and the nullifier, they are public circuit inputs, therefore they are contained within the proof, right? So we just need one argument. And so this contract will have state. As I said, we need to keep track of nullifiers. So it's like I implemented the set as a map where the key is the nullifier and the value is just bool. So if the nullifier was used, it will be true. And the public key. So we use the unsigned 256 type to account for the, so that we can store field elements. In Noir, we are using the BN 254 curve. So the elements from this field fit into this type. And now to the implementation. So first thing that I told you before is we need to verify the proof. So we need to access the verifier contract. But actually, since this contract is stateless, we don't need like instance of this contract. It's enough for just relying on the class hash. And what we do here is we do something that's called library call. So now we use our verifier class hash to access the library for verifying the proofs. Okay, and instead of just calling one contract from another, we do this library call. So it's similar concept to what you have in Solidity in EVM. And yeah, so we call the proof verification, we deserialize the result. So remember, so if the proof is valid, so this will be some. If it's incorrect, it will none. And those will be our public inputs, public key and nullifier respectively. And after that, we will just check two things. So first is that the public key is the one we expect, is the one that we specified during the contract deployment. And second is that the nullifier is not in the set. Otherwise, if it's contained in the set, if it's not in the set, we will add it. And yeah, so that's it. So pretty straightforward. So now the flow will be roughly the same. It just we'll need to declare one more contract, right? So as I said before, we don't need to redeclare the verifier contract, right? But we need to declare our main contract that contains the state. That's what I'm going to do right now. And okay, cool. And then, yeah, I will deploy the contract, copy the address. Good. So things that will change. Sorry. That will change on the upside. Remember that before, when we were interacting with the verifier contract, we were actually calling the view method. Okay. So now we will actually submit a transaction, and therefore we need an account to interact with our network. And what I changed here is that I now introduced an account, and I used again. So I used hard-coded keys here for simplicity. Please don't do that in production. So this is one of the pre-deployed key available in the development network. And once I do that, I can actually submit a transaction and wait for inclusion. So yeah, I will just update the contract address and yes, run the app. Okay. And so note that for all the steps, so there are logs in the development console, so you can check the witness, the proof, the call data, and finally the transaction hash. So yeah, everything is good. So we just have submitted the proof on chain, and yeah, it was accepted. Just like to show you that if I try different secret key, it like the proof will be rejected because on the contract side, yeah, so it is rejected. Oh. Similarly, so if I try to use the same input twice, like now, the proof will also be rejected. Yep. And right, so we are running out of time. So there is a third step that I invite you to try on your own, and it's about how we go to the public testnet and connect the wallet. So it's nothing like really complicated. You will just need to figure out how you create new accounts and fund it from the faucet, like etc. But it's quite easy. So to sum up, what we have achieved, right? So now we have like a proper privacy application with the Noir part on the client side, with the proven in the browser, and we have on-chain part, which is a Cairo contract that keeps some state, and everything is glued together with Garaga. Right. Yeah, if you have this scarp format error, that's okay. It's just like because there is mismatch in the tool versions, so it might error, but it doesn't matter really. So it's all right if you see this error. Okay, cool. So I think we can wrap up. So if you have any more questions about the circuits or the Cairo part of Garaga proving, so please ask. Otherwise, I'm available in Noir Discord. So if you have any issues with Cairo or Garaga, so feel free to tag me. So and also we have a support chat for Garaga. We have a support chat for Cairo developers. So regardless of what your issue is, you'll get help. Thank you.
Cool. Thank you so much, Michael. Um, yeah, thank you, Maya. Appreciate the time and the excellent workshop. And
Thank
like
you for
said,
hosting.
guys have any questions in the Discord, be it around deployment on Starknet, Cairo, and especially about Noir, you feel free to ask. And they also have a Discord which I'll share for any like more specific questions. And yeah, you feel free to reach out also to me directly in our Discord. Cool. Thanks, guys. Thanks, everyone.
Thank you. Good luck.
Bye.
Bye bye.